Bird.
A reindeer.
Bird.
A reindeer.
Eagle.
Oh, wait, put food in your mouth. Huh? Stop talking with food in your mouth. Not-
I love it. Okay, well, it looks like everybody's wrapped up, things are straightened up. We don't have anybody absent today, do we? No, so just a bunch of juniors. So we can go ahead and we'll start a few minutes early, and maybe that means some of you can scoot a few minutes early since you drive yourselves. We are going to do a little demo at the end of class. We're gonna have to go outside for it, but it's going to be fun. And it won't take long, but it's pretty cool. All right, so questions first. Did anybody come up with an estimate on your temperatures? Were you guessing? Did anybody even hazard a guess as to what they were? Nobody even.
Our lowest probably like 40 some because we added ice.
Is that on the for the, are you doing Celsius or you're doing
Fahrenheit.
Fahrenheit? So I did a Celsius reading for all of them. So the cold water initially was at 3.7. So this is the thing to remember, like your fridge is set at like, usually a fridge is set at like 34, or it's real close to freezing. It's very, very cold. So that water came out of the fridge. So I had a 3.7 Celsius on the cold water. The room temperature was, sorry, 18.2, which was about right. And then the hot was 42.6. So if anybody wanted to guess, that's where they were. And I don't know what other one y'all mixed up because some of y'all mixed up some different stuff. The cold one that you got, the real cold one, that one came out at a -3, which is interesting. So super, super cold.
Get the ice, not the water.
Could have, yeah. It was very cold for sure. Yeah. And it would make sense for it to be negative because it's frozen and not like right at the edge. So, all right, well, cool. So we're gonna go ahead and do this last lesson of the semester. Last lesson of 2023. Way to go, guys. You survived so far. So far. I do want to go over how the next 2 weeks are going to go because some of you are new and you haven't been through this yet. So next 2 weeks. So next week, you're going to have your test. First off, your unit 4 and 5 are combined because they were short. So you're going to do a unit 4 and 5 test after today, after class sometime. When you come next week, there's no like reading ahead. It's just studying for the midterm. And you're going to do that with the notes in your binder, with the slideshows in Dropbox, and with the Jeopardy. You're going to get yourself very well prepared. So when you walk in next week, you're going to sit somewhere as a group with your lab team, and we're going to play 4-team Jeopardy. Okay, we're going to play all the way through, and we're going to be playing with your level, your class level's team Jeopardy, not the junior level, because there are questions in yours that are not in the juniors, but pretty much everything the juniors are covering, you're covering that plus some. So we're going to play with your level, not their level. And some of the questions are going to be a little different than what they've seen before because theirs is a little different. So there will be things where they will look at you like you have 3 heads because they're like, I never heard that. So you'll be doing that. All right. And then during class, I'll divide you up into 2 teams and we'll have at it again. And basically, we're going to go through it until you guys are like this, getting them all, because I want you to walk out of here feeling very confident that you know what's going on, right? So you don't walk into your midterm feeling like you don't know what's on it.
Did you decide about the note card?
Yes, I'm going to put that in this week's email. So I'm going to allow 1 3x5 note card that you may bring to midterm. You can write on both sides if you want. That's fine. You may have on it formulas, and you may write out the definitions of the symbols or letters in the formula. Like if you want to write, T equals time, you may do that. But you can't write out definitions and you can't write out scientist stuff, just formulas. Yeah.
So like midterm isn't going to be on teacher, it's going to be
Midterm, so that's where we're going. Yep. So when you come in week after next, you may have the 1 card. You're going to have to show me the card. And this is my card. This is what I'm using. Show it to me. I'll probably put a little mark on it. And you're going to hand it in with your midterm. You're going to give it back to me, and I will staple it to the midterm when I'm done with it. So I will be grading throughout the morning. There are only 3 of you that have Jackie, and you guys can come in a little early or whatever, but we're going to start around 10:15. You can roll in at any point then. If you have Jackie, you're going to Jackie first. Okay. And you'll go do her Spanish exam, and when y'all are all done, she leaves, okay? Those of you that don't have Miss Jackie, you're just gonna come straight to me. Now, I'm gonna be at the counter. I'm gonna have your midterms. Your name's already on them. They're already all printed. And there will be a little orange envelope with your name on it. And you're gonna leave the envelope and take the exam. And I'll tell you, when you've left the envelope, that means I know you've taken the exam. Like, I look down, I go, I'm waiting on the following people because their envelopes are still here. You're gonna hand it back to me when you're done. You can sit in there, in here, in the dining room. You can even sit on the stairs. The pub room is where you go if you're finished, and you have to be silent in there, right? You can go in there before if you want a quick review, or you can go in there after. That's fine, but it's quiet in there because people are still working. That's the thing y'all have the hardest problem with, not the midterm, just keeping your mouth shut for let people finish, right? All right, then after that, I'll be working on grading them. Look ahead. There's going to be a note in your weekly email about this too. Look ahead. When you come for midterms, you have to bring something. You have to bring some food. Like, we have a snack that day. We're eating that day while we watch the movie. So bring something. Look, it'll tell you what to bring. Look in your notes, look in your assignments. So after everybody's done with the midterms, we will like straighten up the counter, throw down the food. Everybody will get some lunch. We'll watch a movie, and y'all will leave, and I won't see you till next year. Awesome. I will send you home. My effort is to send everybody home with a little slip of paper that says on it, this is your midterm score, and this is your semester average. Your actual report card comes by email. So I don't have to worry about trying to print them and fold them into you before you leave. But you'll know what the grade is before you go. Questions? Are we good? Good. Ooh, stop to my foot. Awesome. All right. So our last lesson is on thermal energy and matter. I have a nice little, do you see our little warm, look at them. Aren't they cozy? Look at that. In their Christmas sweaters. All right. So temperature. Somebody define temperature for me. Yusuf.
Measure of how hot or cold an object is.
That's one way. What's our more technical definition, Bailey?
Temperature is the measure of how much the particles move around.
Yes. Okay. So it is the average kinetic, meaning in motion, energy of the individual particles in matter. All right. So when you're measuring temperature, what you're really measuring is how much are the particles in this matter moving. Now, you guys know from like third grade science or whatever that, you know, when a material gets warmer, the particles within it get excited, they start moving around, they spread out, right? And that moving around is what causes the increase in heat because of what? What's causing, yeah, you know?
Friction of the molecules.
Friction of the burn. There's friction again. There's our friend, friction again. Yep. So you got friction between all the particles bumping around. That's what increases the temperature. Okay. So thermal energy is the total energy of all the what? What would go here then? PJ?
Wait.
She's looking. She's looking.
No.
Yeah. Do you know, Yusuf? Nobody knows. All right. So it's all particles. Not that hard. So yeah. So it's the energy. It's the total energy of all the particles. All right. Okay. Keeping that in the back of your head. So when you transfer thermal energy from one object to another, Emily, what's this one? That's heat. Okay. Now, if you, some of you did this last week, I think, but if you were to touch that glass table, if you can, there you go, Bailey, and then touch the chair that you're sitting on or the couch that you're sitting on, which one feels colder? Which one feels warmer?
The glass is cold.
Glass is colder. Okay. Now, here's the thing. The glass and the chair are about 71 degrees Fahrenheit because that is room temperature, that's ambient temperature, and that's where they are. The reason the glass feels colder is because it's a better conductor. So it's pulling the heat out of your hand. The heat is that transfer. So as the temperature in your hand decreases when you're touching that, that's why it feels colder to you. That's why if you were to take that hand and then touch it to your other hand, it would probably feel colder now because it had just touched something cold because some of that thermal energy had moved from your hand to the table. So heat is always going to flow spontaneously from hot to cold. That's why when Bailey touches a glass here, her hand feels cold. And that's because the heat is going from her hand to the table. Okay. Keep that in your head always, that heat is going to spontaneously flow from hot to cold. So we'll come back to that.
I like to do that, and I'll catch my mom's neck with like.
Oh, no. That's mean. So what is an increase in the volume of a material due to temperature increase? Okay, Liam.
Thermal expansion.
There you go, thermal expansion. Okay, so expansion means it's getting bigger, right? Contraction means it's getting smaller. So expansion is your increase in volume of a material due to temperature increase. Now we have something called specific heat, and we deal with this in chemistry a fair amount. So specific heat depends on the material, and it depends on the phase or the state of matter that the material is in. But specific heat, as we'll learn in a minute, is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. Yes,
I love that lad.
he's cute, isn't he? He likes his popcorn. Very cute. So as the thermal energy of a substance increases, its particles spread out and the substance expands. Now this came up in lab. The only like common substance that we deal with that has another that follows this rule but then seems to break it is water, right? So as something gets hot, it expands. This is true with water. It expands. You see it vaporize, and you saw that today in your lab. Both the water and the air inside your bottle expanded when you exposed it to heat, and then you could see that expansion by the water raising, right? Because there was more pressure because you're in a closed system inside the bottle. But with water, as most of y'all know, when you freeze water, it also expands, right? Like if you're trying to freeze water in a container, like if you made soup and you're pouring it in containers, you can't fill it to the tippy top, right? Because when you put the lid on it and put it in, it's going to expand and pop your lid off.
That's why you can't reuse water bottles.
Yeah, or soda. Whoa.
I mean, you can like
Oh,
5 minutes. Just
Yeah, just a little. Yeah, just a little. Yeah, but you got to be very careful because yeah, if you put soda in the fridge, that little tiny membrane or that little tiny thin line where the aluminum tab is on the top cannot withstand the pressure inside from the water expanding. Plus it's already under pressure in there, right? So you got double pressure and it just kind of explodes through. And if you've ever accidentally left a Coke in the freezer, you know that it looks like stalagmites and stalactites and it just makes this giant mess, right? It looks like a cave. When you open it up, you're like, oh, I'm spelunking in my fridge because I forgot what I was doing. So yeah, so as you get it hot, it's going to spread out and expand, except water, which is going, and the only reason water expands when it freezes is because it's forming a crystalline structure, so the molecules are locking into place. So thermal expansion is an increase in the volume of material due to temperature increase. Matter expands when it's heated, and this is what makes the liquid in thermometers rise, which you saw today, and it's the reason for joints in the highway. You know, when you're driving down the interstate and your car's going, yeah, you're running over those rubber. There's these rubber dividers in the highway, they're joints. So when they make like interstate pavement, especially, they make it in sections and they're divided with these little rubber strips in them. And that's because that concrete is going to expand when it's hot and it expands into the rubber and it doesn't crack. Is your question?
Is that why sidewalks also have divots in them?
Yeah, sidewalks are divided for the same reason, also because it's easier to pour them in smaller chunks. And, you know, if you've ever poured any large concrete, anything of size, you find that, yeah, they put, yeah, your driveway has sections in it too. And it's because it does expand and concrete is very rigid. So when you have concrete expanding against concrete, it's going to crack. And we don't want our interstates to crack because they're like, you know, billions of dollars. They're expensive. So we need to keep them in good shape. So one of the ways we do that is these little rubbery joints. So thermal expansion is also used in, what is he standing next to? In what? PJ? Not thermometers, what's this thing called on the wall?
Microwave.
You get close. Thermostat. Yeah, they're using thermostats, okay, which contain what we call, it's a bimetal or a bimetallic strip. So it's two metals that are put together in one strip, and then the strip is made into a coil. And I'm going to show you a video of exactly how it works because it's pretty cool. But the metals that they use are going to be metals that expand at different rates because they have a different specific heat. So they expand at different rates. And if one side expands faster than the other side, you get a curve. Okay, so we're going to watch this now. First of all, rule of life if you're around me. Does anybody recognize this gentleman here? This is one of my childhood heroes. This is Mr. Wizard. Yes, also known as, well, Don Herbert's his real name, but nobody called him that. He is Mr. Wizard. Mr. Wizard.
He invited strangers,
Yeah,
children into his
he
house.
did. So this was Canadian broadcasting. So I'm just going to remind you, never speak ill of Mr. Wizard, aka Don Herbert. He's one of my childhood heroes. Now, there is absolutely nothing wrong or strange about random neighborhood children visiting a grown man's house all alone to learn about sciencey stuff. Totally normal. See, it's totally normal. They're just Canadian. That's all. So we will watch Mr. Wizard and this random neighborhood child. If I have like the full series on DVD, if you ever want to borrow, it's awesome. But you can watch them on YouTube. But I'll tell you what, this is legit how it works. It wasn't like y'all come over and do science. It was like some random kid is hanging out with Mr. Wizard and he goes, let me show you how this works, and does a science experiment. And they go, wow, and they go home and there are different random kids there next week. Totally normal. It was the early 80s. You could get away with this. Okay. So he is going to show us how a thermostat works, and it's really quite cool.
You would recognize this, I assume, Dan, right?
Yeah, it's a thermostat that you put in your house to measure the temperature and the heat.
From
Well,
1968.
not only measure it, because there's a little thermometer in here, but it actually turns the furnace on and off, right?
Yeah.
Well, you and I are gonna investigate what goes inside there, and it's based on the idea of bimetal strip. Bimetal, meaning, you know what bi means?
It means two.
Two, right, two metals. In fact, here are two metals right in front of you.
Yeah.
There are two wires made of metal, and I'm going to send electric current through them to heat them up.
Okay,
Heat it down and sight right across those weights that are on the top there.
okay.
And watch what happens when we heat up the two different metals. What's that?
Well, the one in the front, it's sinking down, like,
Right.
making that go
Okay.
down.
Now watch, I'm gonna turn off the current. Go back up again?
Yeah, then right back up to make the same level as.
As it cools off, it'll go back up to the same height as the other. In other words, what I did this for was to show you that metals expand, but different metals expand at different rates. Obviously, the one on the front expanded the most.
Yeah.
right?
Mhm.
Okay, now let's assume, I'm right over here, and light the candle.
Okay.
And let's assume that we take two metals and put them together to form one strip, which is what this is.
Okay,
And light the candle,
Yeah, good job. Woo.
okay? Okay, you put it right down there. Now hold the strip right in the flame of the candle and watch what happens.
it's starting to make an arch upwards, it's making a really
See
big
how it's
arch.
going up?
Look how it's bending.
Yeah, it's getting a lot.
That's because of the heat.
Okay, now you can blow out the candle.
Woo-hoo.
Okay. Now, what happened was we had, that looks like one metal, but it's actually two metals put together, like these two pieces of wood.
Okay,
Okay, now watch what happens if I expand the bottom one. Watch what happens to the whole thing.
Oh,
oh, it's making an arch up right
Yeah, it
here.
makes it go up.
Yeah.
That's why that went up,
I see.
because the bottom piece of metal expanded more. Now let's assume we take this piece of metal and form it into a coil.
Okay.
So go right over here. I have a thermostat all set up on this little piece of wood. Can you find the coil?
Oh, there it is, I think.
Yeah,
It pulls
That's
up
the
a little
coil.
bit.
Yeah, there is a coil made out of that bimetal. And at the moment, notice that there's no current going to the furnace represented by this light bulb. Okay? So we want to cool off the room in order to make the furnace come on. And you do it here with this spray. Go ahead. Push down on the top and out will come a spray of gas and you will cool off the coil. There you go.
Wow.
On to the furnace, right? Okay, now,
Right
this is
on.
the furnace, so turn on the blower and hold it at the bottom. Okay, now the furnace went off.
Yeah, it turned right off.
Now, this time let me handle it because I want you to watch right there, right at the end. See, I put a pointer here?
Yeah.
Right at the end of the pointer, watch right there. Right now, that's a switch and it's open.
Okay.
Watch what happens when I cool it up.
Wow, the switch moved down towards here and
Right.
it
And
expanded.
made it connected, right? Made a connection
Mhm.
and sent current over to the furnace, which now comes on. Now watch what happens to the switch.
It moved up again and the current turned on.
Right. So now you know how the thermostat works. What do you call the thing inside? Slime metal? Right.
Coolest neighbor ever. I would love to live near Mr. Wizard. I would have lived at his house. Nothing weird about that. Seriously, I've seen every episode the man ever made. They're really good too. He does all kinds of stuff. He had one that was, I remember it was, they had a kid standing like on a building and they had at the bottom, they had like grape juice or something in big giant jugs. And they had one straw that was like, normal straw size that went all the way up to the top. And then they had another like straw like this big. And he's like, tells the kid, okay, which one do you think you'll be able to drink faster with? And the kid's like, well, yeah, I mean, right? But he's just seen this child sucking on this massive not getting to go off, right? The little straw one, right? But it's fun to watch. And I think when they did these, I think for the most part, they did a thing where the kids were only but so aware of what was going to happen. So they got like genuine reactions. I'll tell you one, if you want to look up something fun to try with a grandparent or a parent, he has one video where he tells you to make a deal with your parents that for an allowance, they'll just give you 1 penny on the first day. And then they double it. And then it's an exponential exercise, but it shows you just how fast your parents would be paying out like a ton of money. Like it happens very quickly. But it's a lot of fun to watch. It's like I think it was 1 and then you add 1 to it every day. Oh, daddy came downstairs, so we're gonna howl. There we go. Yes. All right, so there goes Mr. Wizard. All right, so when we're dealing with temperature, we measure temperature with different scales, and each scale has a purpose. They're not all the same, and they have obvious differences. So what do we use mostly here? Fahrenheit. And what do we use in science? Yeah, Celsius. Now, Kelvin is used a lot. Bye, have a safe trip. Oh, sorry. Later. Kelvin is used a lot in physics, and that's because of the zero. Yes.
The ideal gas law.
Yeah, very good. So Fahrenheit is used most commonly in the US. Water freezes at 32 and boils at 212. Those are numbers everybody can remember, right?
No. What?
Celsius is nice and easy. 100, 0, everything in between it is a nice even divide, right? Right? And then you get Kelvin. So it's used a lot in physics. Water freezes at 273.15 and it boils at 373.15. But Kelvin has a difference. 0 Kelvin. 0 Kelvin is theoretical, and it's where all particles stop moving. So think back to the definition of temperature being the average of the kinetic energy of all the particles within a substance, okay? Why is it then, what happens at 0 Kelvin as all the particles stop moving, right? So yeah, there's that, yeah. But if you can get to 0 Kelvin, if it's the average kinetic energy, then you're saying there is no more kinetic energy. It's gone because there's no motion, right? Yes.
But that's impossible because you can't create or destroy energy.
Yes. So that's where you get yourself into those little things. So it's a theoretical thing. They have gotten real close in certain lab conditions. Yes. What is it?
They call the atoms 3 billion to 1 billion Kelvin.
Yeah, it was something very, very small. Yeah, they can get it pretty darn small. And then these other two are just not commonly used. You'll probably never come across them. And there are probably others that I'm not even considering here. But something to notice just for functional purposes. So you have, if you're working, with lab materials that are going between freezing and boiling of water, you've got 100 little marks on your thermometer. Whereas in this case, you're going from 32 to 212. So which one of these is going to have more lines on it? The Fahrenheit is, right? So when you say it's 98.6 degrees Fahrenheit, you're being way more specific than 37. See what I mean? Because you got a 0.6, right? So this is like an average of body temperature. That's what this one is, body temperature. What is this one, do you suppose, right here? 21, 69. Did you catch what it was before? Do you know? It's about room temp. Yeah, 21 Celsius is about room temperature. Okay, and then this is where water freezes, right? This is where water boils, and this would be where all motion stops. So you can tell something else by looking at these. Which temperature scale are they basing all the others on?
Celsius?
Yes, why?
Because it stops at
You can tell that you're using Celsius.
freezes at 0.
Yeah, but look at the numbers. How can you tell they're basing it on Celsius? Can you tell?
So Celsius, so Kelvin is always the absolute 0 Celsius is 273.15, and then the 0 Celsius is 0 Celsius on the Kelvin scale is also 273.
Isn't that interesting? Mm-hmm. Yeah. Yep, you caught that. All right. So this is my point. We got nice round numbers here, 100, 37, 21, 0. And then these, not all of these are all that round. Some of them are, like here and here, but most of them are not. That's because what they did is they took Celsius and converted the others to Celsius. Had you started with Fahrenheit and converted the others to Fahrenheit, you likely would not have 69.8. And yeah, you wouldn't see these decimals, right? You'd see a number and then you'd see the others converted to it. So you can tell that they use Celsius here as the basis and converted the others to it, just for the sake of this diagram. So that's the kind of question sometimes that gets thrown at you on an SAT, you know, like that sort of thing is analyzing a diagram or analyzing data. Oh, do you? Oh, good luck. Oh, you did one last weekend? There you go. But that's the kind of thing they want you to be able to do, is take the data and analyze it. So that's a good way to analyze this data, is look at it and go, well, if I was basing all of these calculations on Ramure, I would not put 29.6 as the number I'm going to use to compare things. I would put something close. I'd put 27 or, I mean, sorry, 30 or 28 or 29, but I wouldn't put 29.6. Like, why would you do that? Right? All right. So specific heat. So what's specific heat? What is it? Yes, Yusuf, sorry, wrong kid. Brother. Yeah. What is it?
The amount of heat required to heat an object or heat one direct to one Celsius.
Yeah, so specific heat, the amount of heat needed, amount of energy really, to raise the temperature of 1 gram of a material by 1 degree Celsius. All materials have different specific heat, okay? And we tend to use water as like our basis here. But if you look over here, you can see, like, if you have liquid water or water, like solid water, which is ice, or water vapor, this is how much heat you're gonna need. Zinging this thing, just making noise at me. Sorry, getting texted by nothing. Are you leaving?
Yeah.
I love you. See you whenever, Thursday night or whatever that is. Bye. He's going to Denver again. So everything has a different specific heat, and you need more energy in some cases than you do in other cases to raise the temperature of a material. And this has to do with whether they're insulators or conductors, which we'll come back to. So calorimeters, which we will use in lab next year in chemistry, calorimeters use the principle that heat flows from what to what, Bailey? Hot to cold, always hot to cold, from a warmer object to a cooler object till they both reach the same temperature. If you left your hand laying on that table long enough, the outside of your skin would eventually reach the same temperature as the table. Now, we use this concept that heat moves from hotter objects to colder objects all the time. Sometimes we take it for granted. You know, if we pour heat into a room, that warm air is gonna, you know, it's gonna cause some of the air around it to heat up, and eventually everything will balance out at a nice temperature, right? They use this also. Have you ever watched any of those like forensic shows where they come into a scene and there's a dead body and they take a giant, scary looking thermometer and jab it into somebody's liver? Have you seen that? It's because your liver is nice and deep in your body. And we know heat flows from hot to cold. So if a 98.6 Fahrenheit human being, 37 degrees Celsius human being flops dead, they're going to start to cool down, and the body heat is going to go into the area that is cooler most of the time, unless they're in like a desert where it's real hot. But if you poke that little thermometer in there, you can tell how much heat has left the body, and tell how long the body has not been undergoing aerobic respiration. So, you know, they can estimate, depending on external environmental factors, they can estimate how long somebody's been dead. And we use this to heat up all kinds of materials, and everything is just kind of a given thing. We think of it as a given thing, but it's actually a thermodynamic law. So heat and thermodynamics, this looks like where you want to spend your morning with a cup of hot chocolate. I want to stay there. Heck yes. So thermal energy and states of matter. Ooh, there you go, Liam. I did this one just for you. So all matter on Earth exists in our 3 states that we know of: solid, liquid, gas, and then plasma being a 4th state that it's not stable to exist typically here. We don't see plasma in our day-to-day life, but we do see solid, liquid, gas, right? So physical change from one state to another is called a what? This is an easy one. What you got, Yusuf? Yeah, change of state. Yep. Sometimes you'll hear phase, but yeah, change of state. So matter will change from one state to another if thermal energy is absorbed or released. Okay, picture an ice cube in your hand. As you hold the ice cube, what's gonna happen to it?
No.
It's gonna melt. Okay, why is it melting?
This is the heat from your hand.
Okay, so the heat from your hand, we know that heat flows from warmer to cooler. So the heat is leaving your hand, and how is your hand feeling?
So
Cold. The heat is leaving your hand, it's going to the ice cube, and that is absorbing or releasing. What's the ice cube doing? Absorbing or releasing thermal energy?
absorb it.
Absorbing thermal energy, right? Because it's absorbing the thermal energy, and therefore it is changing state from solid to liquid. Now, let's say you had, this happens to me sometimes, because y'all know I make cakes, right? So sometimes I'm working with sugar, isomalt. You ever, I hope none of you have ever done it, because I've done it more than once, but usually when you're working with liquid sugar, it's 400-ish degrees Fahrenheit, and it's nice and hot. Remember, water boils at 212, real hot? Okay, yeah. And if you accidentally get a little drop of that
Yeah.
molten sugar on your hand,
Okay.
holy moly, but it's going to go from liquid to solid pretty quickly because it has absorbed or released. Released thermal energy. Now, energy, where did it go? Into you. And you're left with a nice burn, right? Okay. So that release of thermal energy is what causes that state change from a liquid to a solid. So yeah.
That rat looks like he's about to face plant.
No, he's got it, man. He's
Yeah.
doing an arabesque.
He's not-
Like,
he's not
eh.
football.
He's got his arabesque. Look at it. Look at that. Look at those lines. He's at almost 90 degrees. He knows what he's doing. This is a pro.
He's not gonna
His
fall.
shoes his shoes look a few sizes too big.
Shoes, man, those are skates. He's got giant feet and tiny ankles. Forgive him. He needs to learn the special shoe tying trick that I have. Tight ones, small ankles.
Really big. And then towards the end, it looks small.
I'm telling you, when you think about what AI can do, it's like, you gotta realize it starts with noise, right? It starts with a picture of noise, and then it starts reducing the noise. It's pretty wild. Yeah.
Talk for a second about how it's just a random pine cone just sitting on in the lake.
It's treacherous. It's a dangerous place to skate. Somebody should have kicked it out of the way. Uh-huh.
No, it looks like the pine cone's frozen in the ice, so if he
It does look like
moves his
It
back
could be.
forward, then he's gonna like.
It could be. I gotta say though, AI has not ceased to amaze me this entire time with these rats. That is
You
impressive.
don't with skates is losing.
Yeah. This is true. You don't want loose ankles. You will cause a major problem. So calorimeters again. So what's the transfer of thermal energy with no overall transfer of matter? Okay, Emily, there you go. Okay. Conduction. Now we have conductors and insulators. So when I asked, touch the table, touch the chair. When you touch the table, it feels cold because glass is a better conductor than the fabric of the chair. The chair is more of an insulator, which is why we make blankets out of fabric. Yeah.
Brownie point conduction.
Conduction. What do you see wrong?
Conduction is
Where are you looking?
Conduction is gases.
Gas
slow
in,
and
In, should say in. Good call. All right. Conduction in gases. Grab it before I miss it and forget it. And 4 years from now, go, oh yeah, duh. Yeah, so conduction in gases is slower. So you've got conduction, transfer of energy, thermal energy with no overall transfer of matter, right? So conduction in gases is slower than in liquids. That's why when you're trying to like heat up a room, it takes longer than if you're trying to heat up a wire, right? Which is a good conductor. Air is not a great conductor. Gas is not a great conductor. Because the particles in gas collide less often, they're not touching each other. Like in a solid, a lot of the times they're in a crystalline structure and they're all kind of locked in place. Your conductors are materials that conduct thermal energy well, and your insulators are materials that conduct thermal energy poorly. So fabric versus metal, right? Did you have a question?
I found it at the brownie point.
Where?
It says we're still on calometers. But it was.
That's okay. Yeah, that's all right. We're still talking about, because this is what you use to measure that kind of conduction. So we would do this we will do this in chemistry next year. We'll use a calorimeter, and they're kind of fun. They're like little insulated metal, like metal boxes, kind of containers. It's pretty cool. You remember them? Yeah, it's fun. So now we have convection. All right, convection. So this is the transfer of, I'll click that one for you. So that's a transfer of thermal energy when particles of a fluid move from one to another. Convection, just remember, it always has to do with a fluid. So then you get convection currents, which are like loops that circulate. So think back to like, you know, unit 2, when we talked about earth sciencey stuff. What was the big thing with convection there? Do you remember? Colin?
In the mantle.
In the mantle causes what, Chloe? Conduction in the mantle.
Oh, yeah,
Yes, plate tectonics. There you go. Plate tectonics. Right. So the force behind plate tectonics are convection currents in the mantle. So he's got this nice little pot of stew that he's probably just started to heat up because he's touching it with his bare hand. So it can't be that hot yet. It's getting a little steamy.
No, he's got invisible gloves on.
He might. Well, you see him in an upcoming image. He's wearing mitts. So he's looking here. He's warming up whatever that is in there. And it's what you've got is, and this is the thing that you have to remember, in a fluid, when you're dealing with convection currents, okay, it is not that the warmer fluid is rising. It is not that the heat is the heated, whether it's liquid or gas, it's not that it's rising. It's that the cooling fluid is denser and is sinking. And when it sinks, it forces the less dense up. Yes.
Why would you put the food in the water if it's not that hot yet?
Well, you put it in before you turn it on.
Yeah, and then the flavors get absorbed.
Yeah.
Yeah.
Mhm.
So you say it's probably not that hot because he has his hands on it, but
Mhm.
it's also steaming.
I can touch a mug when it's steaming. So it's good. Yeah.
Also,
He's
why
not-
is
he's
why
not
is he
touching the
holding his
liquid.
face so good?
He's smelling it. He's not following good lab procedures.
He's not touching.
So our other would be radiation. So a minute, we had conduction, convection, radiation. Emily, what's this? Radiation, yep, is the transfer of energy by waves moving through space. When you come back from Christmas break, we are going to start talking about electromagnetic spectrum. We're going to talk about radiation a lot. We'll talk a lot about waves moving through space, all manner of waves. But earlier today, this little dude, little fluff dude here, found himself a sun puddle in the dining room and just laid down on the floor in a little sun puddle. He's taking advantage, in that case, of radiant heat. These are waves moving through space from the sun, heating up that little spot on the floor, and he's just soaking it up. So,
My dog does that all the time.
yep. So all objects radiate energy. Oh, you're so radiant today. Okay, then you're radiant, right? So all objects radiate energy. And as an object's temperature increases, the rate at which it radiates energy increases. Now, I will tell you this, even if we never turn on a Bunsen burner, even if we do a nice lab today where we had ice and didn't even involve the hot water, when y'all leave, it's typically 4 degrees Fahrenheit warmer in here than it was because you all are radiating body heat. All of you increase the temperature of this big level of this big space by about 4 degrees. They say a good judgment is human beings are about like 100-watt light bulb. These are like 60 watt in these lamps. So 100 watt is good and hot, incandescent, not LED, right? A good incandescent light bulb at about 100 watts, which is, by the way, what you use in an easy bake oven. You can cook food with it. That's about what every human being in a room will radiate heat-wise.
That's why people burn themselves, so.
Oh, yeah. Yeah. Uh-huh.
Why are they reading a blank book?
I don't know. Why do you have so many questions?
Is there anything to draw?
Decide what to ask Santa for, and they're about to write their list.
It's their journal.
They're wearing their Christmas sweaters.
Just look to a new page.
No, they're writing an entry in their journals.
Well, maybe they
Blank
decided
page.
how many
They
pages
don't
are
have a
late.
pen.
So here's our dude.
They're gonna.
They're imagining the story. So here's our dude here, standing on top of his old antique stove. Probably not very safe, but
His foot's very close up.
yeah, it is. But he's got mitts on. So first and foremost, radiation, convection, or conduction under the pot. Radiation, convection, or conduction. Caitlin.
Radiation.
That is radiation. Okay, that is radiation because it's the transfer of energy by waves through space. So if you ever look over a fire or anything that's hot and you see the air above it gets distorted, it gets all wiggly. You can actually see the effect of the waves on that gas. You guys paying attention back there? Because the effect of the waves on the gas, that's the air or whatever above the fire, the light is getting distorted as it passes through due to the change in density for those different areas of the heat waves. So yeah, that's where you get radiation. Now, how about inside the pot with the stew we're cooking here? Okay, Ridley. That is convection. Up and down, up and down. The warmer stuff moves to the top, starts to cool down because it's in contact with the surface, and the ambient air cools down, becomes more dense, sinks, pushes the other stuff up. This is why if you want to heat up something a little faster, you stir it. You're kind of basically like amplifying the effect of the convection and getting everything moving around so it heats evenly. Yeah.
Isn't that what a lava lamp does?
Yes, this is absolutely convection heat going on right here. Up gets that's wax. Wax gets to the top, cools down because it's further from the heat source, becomes more dense, sinks, pushes something else up, right? Right. So convection is a transfer of thermal energy when particles of a fluid, remember fluid convection, right? Fluid, move from one place to another. Convection current occurs when fluid circulates in a loop as it heats up and cools down. And the last one, why is he wearing mitts, James? Conduction, because he doesn't want to get burned, right? So yeah, real close. He's threatening to touch it. If you look, he's not actually, he's right on the edge.
What is he cooking?
Stew, and it looks delicious.
Yeah,
So
it does.
conduction is when heat is transferred from one particle to another without the overall transfer of matter itself. So you have thermal energy moving. So you have this particle moving really, really fast. So then it causes the one next to it to move faster, which causes the one next to it to move faster. Yeah.
That candle's very close to that.
You know, it is. These guys don't have safety in mind, but they really are enjoying Christmas. I mean, look at this oven mitt over here with the snowflake on it. This is cool, right?
Yeah.
I mean, I'm not even that Christmassy. That is awesome. So yeah, so these are the three. Now, if you look in your notes, you'll see a little graphic. It's actually right there at the bottom of your page. Emily, do you see that? Do you mind holding that up? Yeah. Can you hold that? I'm sure everybody sees what it is. See this little pot on the campfire? Memorize that. You might see it on a unit test. You might see it on a midterm. Okay. Be sure you know. Everybody look at my campfire. Yeah. Yeah.
All the buttons are upright, so that all the knobs are upright. So
Well, some stoves are like that.
Yeah.
and it also doesn't give numbers. It doesn't tell you.
You can only get AI to do so much for you, bud. You're asking a lot. All right, so thermodynamics. This is one of those things that juniors will not know jack about, and they'll look at you like you're crazy. So we have the study of conversions between thermal energy and other forms of energy, and we call it, Colin? We call it thermodynamics. This is nerdy stuff, man, okay? If you want to really get into thermodynamics, there are people who spend their lives on this and talk about like getting into your geek. This is the way to do it. So what's the first law of thermodynamics say? All right, Liam.
Energy is conserved.
Energy is conserved. Okay. This goes back to just a minute ago. We talked about conduction, and we said that you're passing the thermal energy from one particle to another, but you're not losing it, right? You're just passing it along. Okay. What's the second law state? Right.
The energy can flow
From
cold objects to hot.
yeah, colder to hotter. And it's done. Whoops. Sorry. And it's done. It only works on the system you're in. Like you always have to remember you're talking about the system you're in. All right, now what's this last one? Third law of thermodynamics. Ridley. Yep, we talked about that, right? Can't be reached because that would mean what happened, Colin? You pointed it out. You're the one that pointed it out.
You can't destroy energy.
Yeah, because energy's got to go somewhere. You can't make it go away. So it's a theoretical thing. Now, there's also one more law of thermodynamics. Milo.
The zero
Zeroth law. Isn't that why there's got to be a good reason I've never bothered to look it up or never spent enough time on it. Why that it just didn't become fourth? Because we want to be weird in science and say zero. But this states
Wouldn't make
that-
sense to me. Absolute
No.
zero law.
Yeah.
Zero.
And this one is sort of a take for granted, but it's basically that if two systems are in equilibrium with each other, then a third system, if it's in equilibrium with one, it's in equilibrium with another. So it's saying like if I have 3 M&Ms here and 3 M&Ms here, and then I put 3 M&Ms in this hand, and I say this is the same number as this, then that means this is also the same number as this. Because
But
if you say this energy is here, this energy is here, this energy is the same as this energy, then it means this energy is the same as this energy, right?
B equals C, C equals A.
Yes. So as Bailey said, A equals B. What'd you say? A equals B, B equals C, so C equals A. Yeah, you can think of it like a little triangle, round and around. So any object that converts heat into work is what? Milo, you wanna do this one again? An engine, heat engine. Okay. And heat not converted into work is called, Chloe? Waste heat. That's kind of a given, right? Of course it's waste. Yeah, it's waste. All right. Now, thermodynamics. But why here? Entropy. Entropy is central to the second law of thermodynamics. We talk about entropy more in chemistry, which states that entropy of an isolated system left to spontaneous evolution cannot decrease with time. So as a result, isolated systems evolve towards thermodynamic equilibrium, where entropy is the highest. Okay, what does that mean? Blah, blah. Okay, here's entropy and why entropy is useful. Maybe. Hello. Okay, here we go.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider 2 small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the 2 solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy. And again, start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
It just explode.
I don't know. I think you got superpowers for a
My
moment.
brain hurts.
Okay, so you kind of got that idea.
You won't be able to learn anything else.
Energy likes to evenly spread itself. Okay, but
Yeah, there's a
Nice
chance
watch
that
someone
objects
explode.
could get even
an
hotter.
infinitesimally small chance. Yeah. So if you're ever sitting around and that happens, I expect, the aliens have arrived or something, because that's not a good sign. So yeah, not a good sign. Armageddon. So you kind of got it, but you don't have it, because there's also, of course, a what if, a but wait. There's a but wait with entropy.
Of course there is.
Always a but wait, right?
When you study physics,
Yeah.
they teach you a bunch of rules. Things like how you can't create energy, you can't travel faster than light. It's like, stop telling me what to do, man. These rules are helpful though, because they give you a framework for how the universe works. Like, no matter how complicated things get, at least it's not a lawless wasteland out there. Except there is one law of physics that's fundamentally breakable, even though scientists don't usually treat it that way. The second law of thermodynamics. To put it simply, this law says that a system will never become more orderly on its own. The amount of disorder will always increase or stay the same. It's a cornerstone of physics, and it tells us how everything from car engines to galaxies should behave. But if you look closely at it, you can see that it's a law that was made to be broken. And for the world of nanotechnology, that could lead to unexpected consequences. Although you might have a pretty intuitive idea of what disorder is, like if you've looked at your sibling's bedroom recently, scientists have a more specific way of thinking about it. They measure the amount of disorder with a concept called entropy. Entropy can be considered a measure of randomness, or how orderly a bunch of particles are. But it can also be considered the amount of energy that's unavailable to do work. Like, imagine running a car engine. No matter what you do, the engine will always turn some amount of fuel into waste, like heat. This is unavailable energy because it can't be used to make your car go forward. According to the second law of thermodynamics, the longer you run your car, the more unusable energy you'll get. In other words, the more entropy will increase. This observation is actually what led to the discovery of the second law in the first place, although it was discovered in the 1800s, so it was about steam engines, not cars. And today, we know that concept applies everywhere. It's why engineers still can't make a perfectly efficient machine, and on a much larger scale, it's why the universe will eventually run out of usable energy. It's even why the layers of milk and espresso in your cappuccino will blend together if you leave the cup out long enough. The two liquids might start out all neat and artistically separated, but they'll eventually become more random and will mix. Essentially, the second law says that entropy will never decrease on its own. Even if you do create order in one system, you'll always create disorder elsewhere, like by generating heat. But for as confident as this law sounds, it isn't bulletproof. If you look closely at why the second law exists, you start to realize that it has a pretty big loophole. At the most basic level, the second law is true because molecules move around randomly due to their thermal energy, and they're equally likely to move in any direction. Ultimately, this means there are way more opportunities for particles to end up disordered than ordered. So disorder is more likely to increase. Think about that cappuccino again. There are probably around a few septillion molecules. That's a 1 followed by 24 zeros in that drink. And there are only a few ways those molecules can be arranged so that all of the milk is on one side and all of the espresso is on the other. So assuming one arrangement is just as likely as any other, the odds of your cappuccino getting more orderly are really, really tiny. But the thing is, really, really tiny is not quite impossible. It could happen. Of course, the odds of this happening for a cup of coffee are so slim that they're kind of ridiculous. And they don't mean much to physicists. That's why the second law can so confidently say that the entropy of a system never decreases on its own. But in reality, that law is just a statement about the statistics of particle motion. In other words, it's so likely for entropy to increase, or at least stay the same, that we can functionally say it does it all the time. Except for small systems, we can't assume that. And by small, I don't mean systems of like 2 atoms. In recent decades, scientists have found that in systems of up to 100 particles, it's not too unlikely for random chance to decrease entropy, just for a little bit. One of the biggest experiments came in 2002. When Australian researchers published evidence for entropy decreasing in a collection of micrometer-sized beads suspended in water. The random thermal jiggling of water molecules was constantly pushing the beads around, and for the most part, as expected, the beads were moved randomly. But then the researchers looked harder, and they found that sometimes, by pure chance, the beads were pushed in a specific direction, causing them to noticeably speed up. In other words, the beads were turning the disordered random heat energy of water into ordered kinetic energy that can do work. And it was all for free. This effect only persisted for a few tenths of a second, but it proves that on a small scale, you can cheat the system, at least briefly. This wasn't the only paper to investigate this idea either. There was another in 2005 that suggested these effects might be present in photosynthesis, and a few more from 2013 and 2016 that explored how this might apply on the quantum level. So it's something researchers are actively exploring. While this might sound like a random technical detail, these studies are actually really significant. Because as nanotechnology continues to develop, we're going to be building things like engines and transistors on these smaller and smaller scales. Realistically, this loophole in the second law doesn't mean we'll be able to make a bunch of tiny 100% efficient engines or anything, but it does mean they might sometimes pick up energy from their environment, or their molecules might move differently than expected. And that's definitely important for us to know. The rules developed back in the 1800s will have to be rethought to control things at these tiny scales. Otherwise, we might be in for some surprises. Thanks for watching this episode of SciShow. If you want to learn more about the laws of physics and how they apply to the world around you, you can check out Crash Course Physics, an amazing series put together by one of our sister channels. You can find it.
So, yeah, the thing about the microbeads moving around is really interesting. So, lots of yada, 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 super geeky stuff, right? But it's really cool. It's really cool. And this is definitely a branch of science that is going to be more and more active. Because as she pointed out, nanotechnology is increasing, right? Like, do you know what the Saturn V rocket is?
Yeah.
Okay, Drew, what was the Saturn V?
Saturn V was a rocket that was used in the Apollo missions. It was the main rocket that was used getting people to the moon.
Yeah, so it's not as big as these new SpaceX rockets, but it's big. If you've ever been to the Space and Rocket Center in Huntsville, they've got one there that you can stand near. It's massive, okay? There's a huge ring that is the computer, and it's basically like almost like it would be like a part of the cylinder, okay? It's hugely tall. It's a massive ring. You have more power in your pocket and your phone than in that computer. Way more advanced. That thing took people to the moon, get people out of the atmosphere into space so that they could go to the moon. And your cell phone is like a gazillion times more capable of doing stuff than that computer was. So we went from computers like that to computers in our pockets. If any of you have been to grandma's house and she still has her old desktop, or maybe your parents have one in the basement where you've got like the monitor and it's like this big, and then you have the CPU and it stands up, or maybe it lays under the computer. They're huge. And look at how small it's gotten. Like phones got so small that now they're making phones bigger again because people couldn't see the screens. And, 100 years ago, if somebody had something wrong in their digestive system, you'd have to cut them open to look. Then we got small cameras. We can go into the little endoscope. Now they got pills you can swallow. The pill has a camera on it that reports back. Things are really, really, really getting smaller and smaller and smaller and smaller. And that's great because it makes a lot of it more portable, more accessible, which is awesome. So they're definitely going to be considering this type of thermodynamics interactions when you're dealing with nanotechnology. Yeah.
I was curious, do they actually make trains shaped like that?
Yeah. Of course they do. Yep. So trains. So now we're going to talk about, we know all this about heat now. So how do we use heat? Okay, here's my little chunky Santa rat. Look at his fat face. So 2 main types of combustion engines. The one that burns fuel outside is Xander.
Me?
Yeah, is your hand up?
Yeah.
Or is it not up? I can't tell because yours is in front of you. Yep, external combustion engine. And then, all right, how about the one that's inside? Lucas, do you want to do this one? No? James. Internal. Okay, so we have internal, external. All right, now, a steam engine like that train is a great example of external. Anybody know how it works? How does a steam engine work? James, do you know?
You have like a fire in the engine.
Mm-hmm.
You need to keep that burning, but then that heats up steam, which turns a bunch of stuff.
Yeah, expands. Yeah, kind of like when we did the Stirling engine a couple weeks ago. We had that running, right? So your heat source is caused by combustion, with burning something, coal or wood, but it's outside of the engine, and basically you're heating stuff up, and that heat is what's causing expansion and compression, usually of gas or water vapor, and that's causing mechanical parts to move. Internal combustion engine. So who here is a permitted or licensed driver? How many of you? Anybody drive an electric car or everybody drive a gasoline car? Okay, gasoline vehicle. All right, we're going to look at how internal combustion engines function. We're going to actually, we're going to do a little demo on internal combustion engines, but at the end of this, and it'll be hopefully a fun way to wrap up the semester because it's kind of cool. But yeah, so this is internal combustion engine is what you're doing when you're dealing with vehicles that are on the road today. That's what you put the gasoline in and it functions inside the cylinder. So we're going to come back to that in a few minutes. But let's look at this. So what do you call a system in a house, for example, that heats many rooms from a central location? Sure. Air conditioning cools it off. And heats it up. Drew? Furnace is what heats it up? All right, Yusuf? Central heating. Okay, that's what we're looking for. All right. So yeah, central heating system. And there are many versions of these, which we'll come back to in a minute. But heat systems use convection usually to distribute thermal energy. There's hot water heating and baseboard heating and forced air. Most of you, yes, question?
Why is he breaking his sentence?
I'm gonna explain that. He's not breaking it. So most of you probably have forced air in your house. Do you have vents? You turn the thermostat and it blows. Okay, that's forced air. That's what most of us have. Some houses, older houses, usually like houses from the 30s, 40s, 50s, 60s, tend to have baseboard heat. Anybody ever get in car with your mom or dad, or even yourself if you're driving now, and it's frosty outside and they turn on the rear defrosters and there are those tiny lines that run through the glass and suddenly the frost disappears? Those are wires with an itty bit amount of heat, just enough to get it so that it's above freezing.
Otherwise you crack it.
Yeah, barely, just a little bit of heat. Okay, that same concept is baseboard heating. So it runs heating element under the floor, so it gets floor nice and hot. Have you got baseboard heating at your house?
Yeah.
It's great. Yeah, in the basement, that's a perfect place for it because basement floors are usually really cold. So that's a perfect place for baseboard heating. They also have some that run along the sides, like where you have trim along, they have it in there. Now, water heating, that's what he's doing, okay? That's when you have radiators. Anybody ever been to a place with radiators? You have? Where'd you go?
At their greenhouse.
Oh, yeah.
Oh, you have them in your greenhouse? Oh, okay, very cool. All right, so
Is the
the aquaponic stuff. Yeah.
technically in the water and then
Yep.
water technically goes into the heat.
Yeah, exactly. So the way radiators work is there's a boiler somewhere, usually in your house, and the boiler does what you think it does. It boils the water, heats the water up, and the water, just like you think about air running through ducts in your house, the water runs through pipes into the radiators. And the radiators look like that. It's this big metal thing with lots of surface area, right? It's got, it's shaped so that they're like a sort of O-shaped with a central piece that runs through the middle, so that all of this kind of, it's like almost like a bracelet that's been squashed and flattened on the sides, so that all of that tubing conduit gets hot water through it. So if you're in a house, you have a boiler. Now, when I was at college, we had a boiler room on campus, because we're talking about buildings from the 1800s, right? So we have a boiler room on campus. It was a whole big facility with a gigantic boiler that always had steam floating up in the air. You could see it all the time, but it pumped hot water through many buildings on the campus. So my junior year, I lived in a little house that was built in the late 1800s, and I had a radiator in my room. Radiators will heat a room beautifully, and it's not that dry heat that makes you want to, your nose, when you turn the heat on at the beginning of the year, your nose gets all dry because it's so dry. It's a nice moist heat, but it's not sticky. You know what I mean? It's a nice, comfortable heat. They're great. They're harder to control. They have a knob on them that you can adjust, but they're definitely harder to control. And they make noise, which is why he has this. They get air bubbles in them. And it makes an extraordinary amount of noise for a little air bubble in that thing. They will go bang, 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 and they bang loud. It sounds like somebody is hammering on it, but you have to hammer on it to make it stop. So I had a rubber mallet just like that in my dorm room, and I'd get up in the middle of the night and smack the thing because it's screaming at me to wake you up. It sounds like a jackhammer. And if you get the bubble to move and it goes on its way, it stops banging. But they're very, very loud, but they're very efficient. Great way to heat a house. Wish we did it more often. You have to, we had boxes around ours that had like a wooden grate on the front, like a pegboard kind of, but it was a little prettier, and a little wooden box around it so you could sit things on it and not be worried about touching it. Because if you touch a radiator, it will burn you for sure. For sure. And this is the opposite idea. It works in cars, radiators in cars. Instead of having hot running through it, they have coolant running through it. So it's the same idea, just kind of the reverse. Yeah. So cooling systems, he has his Christmas pudding is so big, he's going to have to take those racks out. He can't fit that in that little weird fridge with a strange door, but he's trying. So what reverses the flow of thermal energy? Caitlin? Heat pumps. Okay. Heat pumps reverse the flow of thermal energy. So a heat pump is a device that reverses the normal flow. So the normal flow is from hot to cold, right? So we're going to reverse it with the heat pump. So what do you call that fluid that vaporizes and condenses inside of the tubing in a heat pump? Emily. Refrigerant. Okay, so this is exactly what happens in your car radiator. Okay, you've got refrigerant. It runs through. Okay, and it vaporizes and condenses inside the tubing, and that causes a cooling effect. This is the same thing that happens in your refrigerator. A refrigerator is a heat pump. Weird, because you don't think of heat with refrigerators, but a refrigerator is a heat pump. And a lot of people have heat pump, and that's how their house functions. That's how the heat or air conditioning in their house works, is with a heat pump. So they must do work on a refrigerant in order to reverse the normal flow of thermal energy. What refrigerant goes in radiators? Do we know? It's usually water, but there's also antifreeze in it. And that's in there because you don't want what? You don't want the water to freeze. That would be bad. Yes. Oh, I was going to say also, that's typically ethylene glycol. Yeah. And that's one of those things that also, just a weird science fact, they make it a nice bright color so you can see it. But ethylene glycol has a weirdly sweet taste. And it has been used as a poison because you can put it in drinks and people know it's there. Now, I'll tell you one very, very fun story side tangent. My sophomore year, I think it was, of college, I had my Mustang, right? My 65 Mustang. And it had been a while since I'd had an oil change, but I had the oil, I had the filter, I knew what I wanted in it. I just wanted somebody else to do the trouble of draining it and replacing it for me, right? I was busy. So I took it to a shop, drove in, said to the guy, here's the oil, here's the filter. If you could just change it for me, I'll pay your normal price, but I want my stuff in it. He goes, okay. Young dude, tech, walks out there, comes back a minute later. You know how they do this. Once you start driving a car, comes back with the air filter. Ma'am, your air filter is a little dirty. Would you like me to replace it? I'm like, no, I'm driving back home in like a week. I just want clean oil to go home with. I'll change it then. Okay. They always try to sell you on the air filter. They will bring it to you. No joke. Show it to you. Look at it's dirty. So I'm like, no, I'm good. So this man comes back after 20 minutes and goes, okay, well, you're all set. You totally out of wiper fluid. I changed that for you. Now, wiper fluid is water with a little soap, right? Just a little soap in it. And I said, I'm sorry, excuse me? And he's like, yeah, your wiper fluid. I said, I don't have wiper fluid. He said, yeah, you do. Yeah, you do. You do. And I said, sir, if you want to look at my car and tell me where the sprayers are, I'll be fascinated because I've been driving it for years. And if you want to show me where the switch inside is that works on the sprayers, I'll be even more fascinated because it's not there. And I looked at him and said, you put it in the radiator spill bottle, didn't you? And he looked at me like I had 3 heads and then instantly went white because my radiator has a bottle on the side. If there's too much expansion of the fluid in the radiator, it'll come out of a tube and it goes into this spill bottle that's just an overflow bottle. Dude had filled it with soap water. And I looked at him and I'm like, you for real? That's what you did, didn't you? And he's like, I'm sorry, I'll fix it. Pulls my car out in the back, my beautiful car. Goes underneath, opens the hood. Suddenly, it's like the car is peeing soap water all over the parking lot. Bubbles are everywhere. He's like, I promise it won't hurt anything. I'm like, yeah, because nobody ran it for more than 30 seconds. And I said, and next time you replace wiper fluid, check to see if there are sprayers or a dude, it doesn't exist. It's an old car. But hey, you can put soap in your engine. That's the way to do it. Yeah. So refrigerators are a type of heat pump. All right. So what removes heat from air? All right, Liam. An air conditioner. And along with heat, they remove humidity, which is a big, big, big thing. When air contains more moisture, it can retain more heat, right? That's why people say, that's why if you're here, if you live in Georgia in the summer, our summers are nice and warm, just like our days are nice and warm. But if you live in Phoenix, there's a huge drop in temperature between your day and your night. And that's because there's less moisture in the air to retain the heat. Yes.
You operate that oven?
Don't know. Yes.
Is he really planning to eat all of that?
Yes. It's a fridge. All right. Now, I'm going to show you these. And then we're going to go, listen, then we're going to go outside and we're going to do our little experiment. But these are your topics for your 4 and 5. Unit 4 and 5 tests. Now, you guys know these will be placed where you can find them. You don't have to go. You don't have to take a picture if you don't want to take a picture. I'll give you just a minute.
That would be saying if we go through this year. The one on the left page at the bottom. It looks like a
yeah, it looks like Emma. Yeah. So mechanical advantage. Yeah, mechanical advantage, ideal mechanical advantage, right?
Yes,
not
in there.
Actual mechanical advantage, when is it? Less than, greater than, or equal to 1. So get that part straight. Now, here's what you need to do. We're going to go onto the back deck, and I'm going to take this so that it keeps functioning. But if you are not wearing glasses, you need to get goggles. They are outside on the back deck, okay? Because you definitely want your eyes covered for this. Right above your head. Okay, come on out. This is good fun time. All right, I'm gonna put this guy right here so it can see what we're doing. Okay. Hey. So first things first. Let everybody get out the door. All right. First things first. I got a couple things going on here. So nobody here has an electric car. Everybody here has a gasoline-powered car. So then you're probably familiar with gasoline. Okay, regular gasoline. Everybody knows what that is, right? First thing we're gonna do is we're gonna take this little, what is this called? You know, who remembers? Who remembers what this is?
He's backing up.
Nobody remembers what it's called?
Wire mesh.
Wire gauze or wire mesh, and it has ceramic. Okay, they put ceramic in these. You use these in lab when you've got like a crucible or something nice and hot, because you're not gonna cause damage to it. So what we're gonna do first is we're gonna take this gasoline here. All right, and let me get one of these out. These are matches, and they're nice long matches. Okay.
Wow.
Yeah. Safety matches. So let's say I take, why don't you count with me?
1, 2, 3, 4, 5, 6, 7, 8.
Okay, I counted 10-ish.
I did 10.
Okay, now what's gonna happen if I touch a flame to that cotton ball? How is it gonna go? What do you think? Gonna go boom?
More like
You
a-
think?
It's gonna
Uh-oh.
be like a-
Are you ready?
It doesn't.
No.
No.
Okay,
It's a marshmallow.
wait a minute. This goes in your car. Does that look like enough energy to move a car? No, it's not. That would not move a car. Not exciting, right?
going to agree.
Because you're standing in the wind. I mean, look, it's like,
Smoke target.
oh, that's exciting, Miss Danny. Thanks for the amazing demo. Huh? You're impressed?
Not
It's a fire.
Need a bigger gas. Want to see?
Yeah.
That
was amazing.
Bigger gasoline fire.
All right, inside the engine of your car, and I have a video that I'll show you after this. You can see it with a diagram.
Matching the thing of gasoline.
Inside your car, you have cylinders in your engine. Anybody know how many cylinders are in their engine? How many? 6 in yours? How many?
4.
4 in yours?
8.
I got 6 in my van, 8 in my Mustang.
Yeah.
Yeah,
8.
usually between 4 and 8. Powerful cars, sometimes you get to 12. Those are crazy, like super souped up cars.
I want to point out, it did shrink.
It did shrink mostly because what we've done in this case is we have, that's so exciting.
Whoa.
We've decreased a lot of the air volume in there. We've turned a lot of that into carbon, right? It's black, so we know it's carbon. Okay. Now, inside your car, you have cylinders. Okay, everybody agree this is a cylinder? I put a tiny hole in the end of it. You see it? Okay, but this is a cylinder. Do you agree that this is also a cylinder?
Yes.
It's a very short, shallow, but it's a cylinder. So the way your car works is you have a smaller cylinder inside of a larger cylinder. Okay, and when you have combustion, it forces the smaller cylinder up. Okay, and that's what pushes your crankshaft and drives your car. All right, so what we're gonna do here is first step back a little bit. Okay, now
Everything's gonna explode.
Danny, can you please put the match in the thing of gas?
oh no, we're not gonna do that. Now,
Exactly.
here we go. Let's see.
That's exactly what we want to see.
We put 10 in before, right? Let's just do 5. 1, 2, 3, 4, 5.
I go for 10.
I actually didn't mean to do that, but hey.
Let's do it.
Okay. 5.
It's gonna be
Okay,
great.
now, wait a minute. Your car is not shooting straight up gasoline into your cylinders. It's actually mixing it with air, and there's a pressure change that allows the air in there to, the gas in there to vaporize, which just happened. Okay.
I don't like where this is going.
Are you ready?
I love
What is going on?
I love where this is going.
Me too.
Come on. Ooh, earlier there was too much wind. Come on.
Wait, uh-oh. I think I know what's happening.
This is came back.
Yeah.
Wind. Hold up.
You go over
This
here.
did it earlier too. The wind, if the wind's too fast, as it was just now, it'll make. Oh, he's fine. Come on, open up. If the wind is too strong like that, it takes too long and the vaporization is too complete. So let's try it again. Look,
Smoking.
you see it? Not, it's gone, right? Mostly gone? A lot of it evaporated? Let's do it a little faster this time. I gotta make sure I have my match. Match ready. We gotta wait for this wind to quit. Wind.
Gonna be fun, not good.
It's gonna be fun, not good.
If I just stand.
No, you don't wanna do that. 1, 2,
Put it 10.
3, 4, 5. Nope, 5 should be enough.
You got it.
Okay, let's try this again.
Oh my gosh. Oh, this
I
is
knew
so
it.
scary. Sandy, you got to shake it.
Oh, you don't have to turn it a little. Do the thing, wait.
I know it.
This is the whole thing of that.
Again, is that enough energy to move a car forward?
Yeah.
Yes.
So, huh? How did it go? Does anybody see?
All the gas.
Right.
All the gas in there. So I'm like,
It's like over there.
Gas in there, it counteracts it. You need the vaporization. That's the point.
oh.
That's how it works. So
Drops of gasoline.
well, sometimes it's too much.
You
Now
put
you
Now try the whole thing.
You put the whole thing in there. Put more gas. Yes.
I will say that Where's the bottom go? Here, this, if you guys want to give it a touch, it is warm. It's not hot, but it's a little bit warm. Can you feel the heat? Just a tiny bit. It's just a little bit warm. Because that heat did get transferred. Some of it got transferred. You feel it? So it's just a little bit warm.
Pour the whole thing in there.
And you can see a little, there's some remnants of combustion in there that's not clean. See the soot?
I want to see the metal actually wake.
No, I don't want to break it. Because I want to do that again because it was fun.
Put
All right,
more
let's
gas
go
in
and I'll show you how combustion engines work a little closer and then you guys will be set to go. You know?
there. Put more gas in there.
Fun or what?
Yeah, put more gas. Put all the gas in there.
I love the big sound, right? The big sound is
Look at this, how much you do this?
yeah.
Up, boom.
Mhm. Kaboom, kaboom. Alrighty, thank you, Sure. So lastly, so how do they work? This video is a little bit longer, but it's cool. If you have to split before it's over, feel free, just walk out quietly so you don't distract those who are watching. But this is 2-stroke versus 4-stroke internal combustion. Maybe. Yep. I'm not outside anymore. Stop acting crazy. Wait. Buffer. What is the deal? Buffer.
If we observe the
Actually, hold on 1 second. Let me do this. I'm out of there. I'll put it straight into YouTube so it doesn't get stupid for me like that. No.
So here we have a
No,
okay.
you're gonna be dumb. You don't have anything. Okay. There, that's convection for you, by the way. That's video Jason gets of the river in the mornings. It's pretty cool. It's kind of mesmerizing. Okay, here you go. Oh no, we got a commercial though. We always have a commercial if I go to YouTube, which is why I do it inside the slideshow, but then it gets bumpy. All right, there we go.
Here we have a 4-stroke engine.
Mm.
And here we have a 2-stroke engine. If you observe the
Sorry.
first glance, they seem very simple.
Yeah, no, break everything.
They both have cranked and they crank that, get where they can rock. As well as a whip spin and a piston. They also both have a cylinder. And they both operate by converting the reciprocation of the piston into the rotation of the crankshaft, which then turns the gears of the transmission and ultimately the wheels of the vehicle. But beyond these core similarities, the 4-stroke and the 2-stroke start to fundamentally diverge, resulting in two very different approaches to internal combustion. And what I'm going to do today is give you the only video you need to watch to get a very solid understanding of how a 4-stroke and a 2-stroke engine work. We'll also be exploring the differences, benefits, and drawbacks of each engine type. And this will then answer the question of why the 4-stroke ultimately prevailed over the 2-stroke in most applications, despite being larger, heavier, more expensive, and more complex. So let's get started with the 4-stroke. Why is it called a 4-stroke? It's because the 4-stroke engine needs 4 strokes to complete one combustion cycle. Every time the piston moves from top to bottom, or vice versa, that's 1 stroke. The piston equals 180 degrees of crankshaft rotation. Now the 4 strokes are intake, compression, combustion, and exhaust. During the intake stroke, the piston travels from top to bottom, which are also known as top dead center and bottom dead center. As the piston does this, it creates an empty space or vacuum inside the cylinder. This newly created void is essentially a brief absence of air. And because we have an absence of air, we also have an absence of air pressure.
In other words, we have a low air pressure inside the cylinder and atmospheric air pressure outside the cylinder. This air pressure difference cannot continue to exist, and air naturally seeks to equalize pressure everywhere. And so air, together with fuel from the outside, rushes into the cylinder and fills it with a fresh air-fuel mixture. By the time the piston reaches bottom dead center, all the air and fuel that can hope to get in have done so, and the piston now starts to move upward. As it does that, it forces the air-fuel mixture into an ever smaller space. In other words, it's compressing the air-fuel mixture, which is why this stroke is called the compression stroke. Just before the piston reaches top dead center, the spark plug fires and ignites the air-fuel mixture, which finds itself between the two electrodes of the plug. Although combustion inside an engine is often described as a bang or explosion, that isn't what's actually happening. An explosion is detonation, which is a rapid, uncontrolled process. In contrast to this, combustion is deflagration, which is a much slower, more even, and controlled process. Combustion spreads out evenly outward from the spark plug through heat transfer. The small portion of air-fuel mixture initially ignited by the spark plug heats up and ignites the next layer of the air-fuel mixture. This layer then ignites the next layer, and the process continues until all the air-fuel mixture is burned. As the combustion flame front spreads, it rapidly raises the temperature and pressure inside the cylinder. Because the cylinder is sealed, this pressure has nowhere else to go, so it ends up pushing the piston down the cylinder with great strength. This is our combustion stroke, and after 4 strokes, this is the only one that actually generates power, and it does so by converting the energy released by combustion into motion of the piston, which then turns the crankshaft and ultimately the wheels. By the time the piston reaches bottom dead center again, all the air-fuel mixture has been burned, and we now have exhaust gas, or the remains of combustion, inside the cylinder. As the piston moves up once again, the exhaust gases will leave the cylinder and exit through the exhaust piping, catalytic converters, and mufflers out into the atmosphere. Now, if you know a bit about engines, then you've probably noticed how my explanation of the 4-stroke combustion cycle fails to answer some very important questions. And these are: how do we allow air and fuel to get in during engine? How do we keep air and fuel as well as combustion energy from escaping during compression and combustion? And how do we allow exhaust gases out? Well, the answer to all of this is the same thing, and it's valve. The intake valve opens during the intake stroke to allow air and fuel into the cylinder. Both valves are closed during the compression and the combustion stroke to prevent air and fuel as well as combustion energy from escaping the cylinder. And finally, the exhaust valve opens during the exhaust stroke to allow exhaust gases to escape the cylinder. Now, the valves are operated by the camshaft, and as you can see, the camshaft has the lobes on. As the lobe contacts the rocker arm pushes onto the valve and opens it. As the lobe releases the rocker arm, the valve spring ensures that the valve returns to its seat as soon as possible. The shape of the lobe determines how much the valve opens and how long it remains open. The higher the lobe, the more the valve opens, or the more lift we have. The broader the lobe, the longer the valve remains open, and the more duration we have. But for the engine to run well, we must ensure that the motion of the camshaft is synchronized to the motion of the crankshaft and the piston. This is done by a cam belt or cam chain. It connects the crankshaft with the camshaft to ensure that the correct valve opens during the intake, that both remain closed during compression and combustion, and that the correct valve opens during the exhaust. As you can see, our chain is very slack, and this is because our display model doesn't have a chain guide and tensioner, which are normally present to ensure proper operation of the chain. As you can see, the 4-stroke engine needs a lot of mechanical parts to get gases in and out of the cylinder. These parts are a source of weight and complexity, but also of friction, and they actually have to steal some of the engine's power to operate. As you can see, I need some strength to overcome the resistance of the valve spring and open the valve. This strength must come from somewhere when the engine is running. And so the valves actually steal a bit of the energy created by combustion to open themselves and allow the next combustion to happen. Additionally, all of these mechanical parts are a source of potential engine failure. If they aren't installed correctly and the timing of the engine isn't correct, it can result in the engine running poorly. In extreme examples, the timing can be so off that it results in the piston contacting the valve on an interference engine. An interference engine is one where valves and the piston occupy the same space but at different times. This can often enable a more compact, efficient, and powerful engine, but it also leads to engine failure in the event that the chain or belt snaps. Now, if we move over to two-stroke, we can see that it replaces all of this with just this. In the case of the four-stroke, this is the cylinder head together with the valve cover, whereas in the two-stroke, we really have just a cylinder cover or cap. There are zero moving parts, no valves, no chains, no cams, no springs, and therefore less weight, less complexity, less cost, and less potential for failure. So then how does the two-stroke get gases in and out of the cylinder without valves? Well, if there's one thing you should take away from this video, it's this. The four-stroke only uses the area above the piston for the combustion cycle, whereas the two-stroke uses both the area above and below the piston. In other words, the intake charge or air and fuel mixture see both the area above and below the piston in a two-stroke, whereas the intake charge never gets below the piston in a four-stroke. Now let's observe the combustion cycle in a two-stroke. And we're starting with the combustion stroke itself and the piston atop its center. So combustion has just started. It's building pressure in the cylinder and pushing the piston down, while at the same time we have fresh air fuel mixture below the piston. And I'll explain how it got there in just a moment. Now, as the piston is going down, it opens up the exhaust port, which allows some of the exhaust gas to start escaping from the cylinder. And at the same time, the downward motion of the piston is also compressing the air fuel mixture below it and pushes it into the transfer port, which is still blocked up by the piston skirt. As the piston goes down some more, it starts to open up the transfer ports, which then allow the compressed air fuel mixture from below the piston to be transferred above the piston. The pressure in the cylinder has already decreased substantially because much of the exhaust gas has been allowed to escape through the exhaust port. This means that the compressed air fuel mixture coming out transfer port is actually at a higher pressure than the remaining exhaust gases in the cylinder, which means that as the air fuel mix enters the cylinder, it helps to push out the last of the remaining exhaust gas. But as you can see, our exhaust port is still open. It's not blocked up by the piston, which means that the air fuel mixture not only pushes the remaining exhaust gas out of the cylinder, the air fuel mixture itself is also free to exit the cylinder through the exhaust port. This brings us to the first drawback of the two-stroke. The design of the engine means that some fresh, unburned fuel gets dumped out of the exhaust. This, of course, is the definition of inefficiency, but there are ways around it, and we'll cover them in this video. So the piston is now at bottom dead center, and we have an air fuel mixture above the piston as the piston starts going up. Now, in addition to pushing up and compressing the air fuel mixture, the upward motion of the piston is also drawing more fresh air and fuel into the cylinder. As the piston rises from bottom to top, it creates a vacuum below the piston. Just like in the four-stroke, vacuum is the absence of air which cannot continue to exist. And so the air fuel mixture rushes into the cylinder through the intake port and occupies the area below the piston. When the piston reaches top dead center again, we have compressed air and fuel above the piston, ready to be ignited, and fresh air and fuel below the piston, ready to be pushed into the cylinder when the piston descends again and opens up the transfer port. The two-stroke combustion cycle and design also explains why the two-stroke piston is much longer than the four-stroke piston. It must be long enough to keep both the transfer and the exhaust port blocked up as it travels and approaches top dead center. If the piston were shorter, exhaust gases could enter the area below the piston, but more importantly, the fresh intake charge could also escape out the exhaust port with the piston at top dead center. As you can see, each time the piston is at top dead center, a combustion event occurs. This also explains the name two-stroke. The engine only needs two piston strokes to complete its combustion cycle. In other words, each 360 degrees or one full engine revolution results in a combustion event. Whereas in a four-stroke engine, combustion occurs only every other time the piston reaches top dead center. Combustion occurs only every 720 degrees of engine rotation. This means that the two-stroke produces twice as many combustion events or power pulses for the same RPM, which means that in theory, the two-stroke engine can make twice as much power for the same displacement compared to a four-stroke engine. The other important thing to note is that the strokes are very clearly defined and separated in a four-stroke engine. Each completed stroke of the piston marks the beginning of one and the end of another stroke of the combustion cycle. But the two-stroke engine sort of lumps the strokes together. They overlap and occur simultaneously. The two-stroke is actually multitasking, which enables it to squeeze more action into the same time. But as with everything, there is a price to be paid. My explanation of the two-stroke combustion cycle probably raises a question mark. For example, what if a big case involving the exhaust port, or how come the downward motion of the piston doesn't just push the air fuel mixture back out through the engine? Well, no worries, we're going to answer these questions one by one, and their answers will shed light on the price that the two-stroke paid for its increased combustion frequency. Let's start with how we prevent air and fuel from going back out the intake when the piston goes down. To do that, many engines use this, and this is a reed valve, which is placed into the intake. Alright, so a reed valve is essentially a one-way valve. It allows gases to enter, but it prevents them from exiting. When the piston moves up and creates a vacuum inside a crankcase, it also creates a low pressure zone inside the crankcase, while a high pressure zone remains outside in the atmosphere. This pressure difference forces the reed valve blades or pedals open. Vacuum inside the crankcase means that there's very little pressure acting behind the pedals, but there's atmospheric pressure acting on the other side of the pedals, forcing them open. When the air-fuel mixture enters the crankcase, the pressure soon equalizes. As the piston starts going down and compressing the air-fuel mixture, pressure actually becomes greater behind the pedals on the crankcase side, forcing them shut. The design of the reed valve is such that the pedals can only open in one direction, and so crankcase pressure closes the pedals and keeps the compressed air-fuel mixture from escaping back into the engine. Now, the elephant in the room that we have to address next is lubrication. If you have ever owned an engine in any kind of vehicle or appliance, then you probably know that lubrication is key for engines. Without the protective film of oil, metal-to-metal contact occurs and quickly leads to catastrophic failure. As you may know, in a four-stroke engine, everything under the rings of the piston is constantly lubricated by engine oil. This engine oil is also usually circulated, filtered, and pressurized by an oil pump to ensure that the film of oil between metal surfaces is always strong enough to resist all the forces which are trying to break it apart. So the elephant in the room is the area under the piston inside a two-stroke engine. If this area constantly sees air and fuel, then how do we keep it lubricated? Obviously, getting the same quantity of oil here as in a four-stroke and keeping it circulated is impossible. It would end up in the combustion chamber and probably prevent combustion from ever occurring. We also know that fuel is a solvent, making things even more difficult for the rotating assembly of the two-stroke. So then, how do we prevent metal-to-metal contact in a two-stroke? Well, the answer is a compromise. Instead of only getting air and fuel under the piston, we get air, fuel, and oil in here, but we keep the quantity of oil low enough to prevent it from impeding combustion, but high enough to provide some lubrication to the moving parts of the engine.
What color?
Whatever the holiday is to you, get the most out of it. In a few months, be hot.
Can't get paid for it. You get paid for it.
Well, visit the local holiday.
Hey, Dawn. It's only got a couple minutes left, but like I said, if you,
There
oh,
are two
well,
possible
it's not
ways to
halfway,
get
but you can go if you need to
lubricated
go. It's no big deal.
two-stroke oil into the engine. The only method is
Like
to
leaf
remix the oil with the fuel that comes into the tank. The second, more modern method is to have a separate tank for the two-stroke oil and have an injection pump which injects the oil into the engine, usually into the carburetor, where it mixes with the fuel and air and ends up inside the engine. Now, the ratio of air to fuel inside the engine is usually somewhere around 13:1, and the ratio of two-stroke oil to fuel is anywhere from 24:1 to 50:1. This gives you an idea of just how minimal the amount of lubricating oil is inside the engine at any one time. Because it's mixed together with the air and fuel, the oil also inevitably ends up inside the combustion chamber where it gets burned. This is where the smoke and the smell of two-stroke engines comes from. Two strokes essentially burn small amounts of oil all the time. This is also why the lubrication system of two-stroke engines is known as a total loss lubrication system. The oil never gets reclaimed like a four-stroke. Instead, it's lost and topped up as necessary. This means that the lubrication of the rotating assembly of a two-stroke isn't nearly as consistent or reliable as an four-stroke engine, which ultimately leads to a significantly shorter maximum potential lifespan for a two-stroke. No amount of maintenance or lubrication quality can overcome this inherent design constraint, and the average lifespan of a two-stroke engine on a motorcycle is somewhere around 15,000 to 20,000 kilometers. Some may do more than that, but many won't make it even that far and will need their pistons replaced and bottom ends rebuilt well before that. Racing two-stroke motorcycles often need rebuilds after only 15 to 20 hours of operation. In contrast to this, four-stroke engines on motorcycles, even small ones, can make it to 50,000 kilometers. Some even get to 100,000 kilometers and beyond, whereas engines on cars and trucks regularly make it past 300,000 kilometers. Some even get up to 1 million. The flip side of this is that although two-stroke engines require more frequent rebuilds, their rebuilds are usually much less expensive and far easier to perform. The other problem with a total loss lubrication system is that burning oil is obviously very bad for emissions, which is the key reason why many legislations around the world have outlawed the manufacture of street legal two-stroke vehicles and only allow off-road and competition two-stroke vehicles to be made and sold. The difference in lubrication systems between the two engines is also embodied and evident in the piston rings. The four-stroke has 3 rings, whereas the two-stroke only 2. The third set of rings in a four-stroke are oil control rings, and they prevent oil from getting into the combustion chamber. Oil control rings are obviously unnecessary in a two-stroke because the oil gets into the combustion chamber anyway, with or without them. But there's a benefit for the two-stroke here because less rings means less friction and less power losses due to this friction. But the piston rings don't just differ in number. They're free-flowing or allowed to rotate in the four-stroke, whereas in the two-stroke they are pinned in place using split pegs. Now these pegs are missing from this particular piston, but you can still see the holes where the little pegs or locating pins go. Their purpose is to prevent two-stroke piston rings from rotating. This is done to prevent the piston ring ends or gaps from snapping onto the exhaust or the transfer ports, which would lead to engine failure. Instead, the rings are fixed to ensure that the gaps always travel over the area between the transfer ports to eliminate the possibility of getting snapped by the ports. The free-floating ring system of the four-stroke is actually superior because allowing the rings to rotate can help ensure more even wear of rings and a longer-lasting engine. The lack of consistent lubrication is also why two-stroke engines often use ball bearings and or roller bearings as their rod and crank bearings. Ball bearings are more expensive and require more space than plain bearings, but they're far more resilient to poor lubrication environments. On the other hand, most four-strokes can use plain bearings, which are very small and inexpensive, and which together with a good film of oil offer excellent load bearing capacity and higher shock resistance. But our example four-stroke engine actually uses ball bearings too. The reason is that this is a very compact and inexpensive engine, which has a very small oil pump that isn't able to provide the kind of lubrication that oil pumps on larger, more advanced four-strokes can. Another area where two strokes are limited is the compression ratio. The compression ratio of the engine is the ratio between the largest and the smallest volume of the cylinder, or the ratio between cylinder volumes when the piston is at bottom and top at center. The higher this ratio, the more we compress the air-fuel mixture, leading to the air and fuel molecules being packed closer together, which then improves combustion speed and strength, leading to higher efficiency and power. Now, both of our demonstration engines are actually single-cylinder 125cc motorcycle engines. Our four-stroke is from a 90s Honda Spacie scooter. It makes 10 horsepower and 10 newton-meters of torque and has a bore of 52.4 millimeter and a stroke of 57.8 millimeter. Our two-stroke engine is from a Yamaha DZR Belgarda sports bike, which is also from the 90s. It makes an impressive 28 horsepower and a less impressive 16 newton meters of torque and has a bore of 56.4 and a stroke of 50 millimeters. One of the reasons why the four-stroke engine looks very underpowered is because space constraints in a scooter lead to restricted intake and exhaust design. The other reason is that the scooter engine is focused on economy and user-friendly power, whereas the sport bike engine is focused on building peak power, which advantages to build and hold over only a very narrow part of the top of the power plant. Although both engines have similar bore and stroke specs, they have very different compression ratios. The four-stroke engine has a compression ratio of 9.5 to 1, whereas the two-stroke engine manages only 5.9 to 1. Why is this the case? Well, the reason is very simple, and it's because the four-stroke utilizes the entire volume of the cylinder. Compression begins when the piston is at bottom dead center and ends when the piston reaches top dead center. Things are different in the two-stroke. Compression does not begin at bottom dead center. Instead, it only begins when the piston closes off the exhaust port. Before the exhaust port is closed off, the cylinder isn't sealed, and air and fuel can't be compressed. Instead, they're free to escape from the exhaust port. This is why in a two-stroke, the compression ratio or the ratio between the largest and the smallest cylinder volume is the ratio between this and this volume. Obviously, this is much smaller than this, and leads to a much lower compression ratio, which ultimately limits efficiency and performance in a two-stroke engine. The final difference is that the four-stroke is inherently more flexible thanks to its more complex, bulkier design. And the key factor behind this lies in the camshaft. A camshaft is essentially the mechanical brain of the engine, and changing the camshaft can completely transform the character and performance of the engine. But you don't even need to change the camshaft. You can simply shift its angle in relation to the piston, which is known as advancing or retarding the camshaft to impact the engine forward. And this can be done while the engine is still running. Most modern engines on cars incorporate variable valve timing systems, which advance and retard camshafts as required to produce good responsiveness and torque at low RPM and good power at high RPM. Many systems even pack multiple load profiles into a single camshaft and can switch between them during engine operation, giving us a low valve lift at low RPM and high valve lift at high RPM, which further improves responsiveness, power, and torque throughout the rev range. In contrast to this, the two-stroke cannot change the position of its port. They are a fixed part of the engine's construction. So a two-stroke can usually change the size of the exhaust port. And this finally brings us to the big round hole in the exhaust port. It's meant to house this. And this is a part of a system called YPPS, which stands for Yamaha Power System. Other manufacturers also develop their own system with their own acronyms, but all these systems have the same goal. And despite what their name is, the goal isn't to increase power. Instead, the goal is to even out the power band of the two-stroke, resulting in a smoother, more usable, and more linear power band and power delivery. Our particular example is what's known as a guillotine-style power valve, and it rotates to make the exhaust port smaller at low RPM and larger at high RPM. Now, the power valve works together with another signature feature of two-stroke engines, and that is the expansion chamber present in the exhaust. Now, the expansion chamber relies on the principle of wave resonance, which is similar to what you experience when your voice creates an echo. When the initial acoustic wave of your voice encounters an obstacle, it gets reflected back as a delayed, weaker acoustic wave. The exhaust pulse coming out from the engine is also essentially a waveform. And when it encounters the change in diameter created by the expansion chamber, it reflects another waveform back to the cylinder. This waveform can then be designed to push back the fresh air-fuel mixture that's trying to escape through the exhaust port. Now, at low RPM, the piston is moving slowly, and this means that the reflected wave from the expansion chamber can easily make it in time to push the fresh air-fuel mixture back into the cylinder. This is why we don't need the entirety of the exhaust port and can reduce its size. The benefit of the reduced exhaust port size is that during combustion, we keep the cylinder sealed away longer, which means that we can harness more of the combustion's energy, which results in better responsiveness and torque at low RPM. As RPM increases, the piston moves faster and faster, and so there's less and less time for the reflected wave from the expansion chamber to make it back to the cylinder and push the air and fuel back in. So we increase the size of the exhaust port to buy more room and time for the reflected wave to take its bank. We do sacrifice the increased duration of cylinder sealing, but we're already at high RPM, so building power and torque really isn't an issue at this point. So it seems that we reduce lifespan together with high emissions and poor efficiency spell review for the two-stroke. Well, there's a glimmer of hope in the future of two-strokes, and it comes in the form of direct injection. Direct injection basically means that we're spraying fuel directly into the combustion chamber via an injector, instead of bringing it in from the intake port via a covering. Direct injection also has benefits for four-stroke engines, and many modern four-stroke engines in cars feature direct injection. But the benefits of direct injection are more significant in the case of two-strokes. By spraying fuel directly into the chamber, we can start introducing the fuel only when the exhaust port gets closed off by the piston and compression action begins. This prevents fresh fuel from being dumped out the exhaust port, which obviously dramatically improves efficiency and emission. It also removes the solvent properties of fuel from under the piston, which can help improve the lubrication of the rotating assembly. However, there are some challenges to implementing this technology, and it's still in the development stage. And only time will tell if and when it will become a mass production reality. And there you have it, two seemingly similar but actually very different types of engines, each with its own benefits and drawbacks, which I hope this video managed to explain in an understandable and illustrative manner. As always, thanks a lot for watching.
Hey, y'all,
Everything is
you wanna
good.
hear
And you
Let me
can
stay.
on the detail.
Yeah. You like to work on cars?
We
No?
don't really have cars anymore. Got a minivan like that.
Project cars are gone, well, if you ever want to, let me know, I can pull the stang out, and let you piddle around in there, you would be the only one who's done it. Bye, y'all, see you next week. Alexa, turn the television off.